So today we are going to look at the final examination for semester 1, session 2022 and 2023. Okay, so we can look at, so you still have the part A and part B. So part A is objective questions and part B is the subjective questions. So let's look at the questions. So the following are two governing law of electrostatic field. So electrostatic are the topic of our chapter 1. So we mainly focus on the Gauss law and also the Coulomb's law. So the answer is 1, 3. Right. So dielectric strength, dielectric strength is maximum electric field that a dielectric could tolerate without electrical breakdown. So dielectric breakdown occur when, so the first one, the dielectric become conducting. So this is true when the dielectric breakdowns. So the atom, it can fully move within the charge. The charge can freely move in the dielectric. So they become conducting. So this one is correct. And then second, electric field in the dielectric pull electron completely out from the molecule. This is what happens when they pull the electrons completely out. It means that the electron now can move freely. So this is correct. The third one, the molecule in the dielectric are too weak to hold the electric field average acceleration. So this statement is not correct. So number 4 is molecules are polarized. So this is correct. When they are exposed to the electric field, they will be polarized. So the answer is 1, 2, and 4. So we look at next one. So electric field, that exists in a region consisting of two different medium which satisfy the interface spacing. The medium condition can be solved by using boundary conditions. So the boundary condition at an interface separate the following except, so we study about the boundary condition between dielectric and dielectric, right? So this means that these two dielectric has different dielectric constants. So it is possible to study the boundary condition between them. Dielectric and conductor, yes. Conductor and free space, yes. So we never study about the boundary conditions of conductor and conductor. So basically conductor and conductor, they are the same thing. So there is no boundary between them. So except the question is asking you about except. So the answer is D. So we look at the question number 4. Question number 4, a coaxial conductor is illustrated in the figure. So it has the inner and outer radius of A and B. So we use the Gauss law, to find the electric field and the potential difference. See, the electric field is given. The potential difference is also given for these coaxial conductors. So the capacitance of the coaxial conductor can be obtained from the formula. So it's asking you about what is the formulas of the capacitance. So the general equations of capacitance is Q over V, right? General, regardless whether it is a parallel plate or a spherical capacitor or cylindrical capacitor. So you will still use these equations. So the Q has been given by the questions, right? So if we put the V down here, it means that it will be 2 pi epsilon L over Q and ln B over A. So you can simplify. So you can see your answer is equals to what? To A, right? Equals to A. So this is a capacitance of these coaxial capacitors. So we have external electric field highly affect the electron, okay, and protons of a dielectric material. So when the direction of the E is along the positive y-axis, okay, the protons are displaced to the what direction of the E and from their equilibrium position. Okay, so this is the case. Just imagine when you have a dielectric. So under normal conditions, okay, so the electron and proton, okay, they are freely move, okay, inside the dielectric. Can be here, can be there, okay, freely move. When the electric field come, something like this is the direction of the electric field, whereby in the question it mentioned that it is a positive one. When the electric field come, okay, so you will see that the electron and also the proton, they are not in these conditions anymore. Okay, so they will align with each other. They will align. So you will find that the negative charge will all be here, okay, and the positive charge is all here. Why they arranged in this way? So if you remember, the electric field from positive charge is outward and terminate at the negative charge. So just imagine here you have a positively charged items, okay, positively charged proton, and here you have electrons. So the electric field will be in these directions. So positive and negative, okay, they attract each other. That's why all the electrons, they will align on the left hand side, whereby the proton, they will align at the right side. Okay, so the question is, okay, the proton are displaced in what direction of E? So you can see the proton is moving to the right side, right? So moving in the same directions as the electric field. Okay, so the answer is B. Okay, so if the z-axis carries a filament current of 10 pi ampere along the z directions, which of the following is not true? It's not true. Okay, you have to find the wrong one. Okay, so here you have to find it out. You have z-axis, so maybe you can here. Okay, so you have a z-axis, so you can draw your axis. You have a z-axis. Okay, so the current is along the z. Okay, so this one is your current filaments. Okay, your current filaments. So flow along the positive z direction. This is your I. Okay, it doesn't mention about the length, so we assume that this one is an infinite line. Okay, so ask us to find the H, right, the magnetic field at different positions, right? So we can look at the first one. Is asking us to find the magnetic field at 0, 5, 0. Okay, 0, 5, 0. So 0, 5, 0 is over here. So this is 0, 5, 0. The observation point is 0, 5, 0. Okay, so what is the magnetic field? So for infinite line, okay, the equation will be I over 2 pi r and phi. Okay, so first thing is to find the distance. You define the point T, if you still remember. So this one will be your point T. So your point T will be at the position 0, 0, 0. Okay, right. So obviously, okay, your r is equals to 5. This is the distance. The 5 distance. Okay, and for this one, okay, you can replace the value. For example, the I is 10 pi. Okay, question mentioned it is 10 pi. Okay, then you have a 2 pi r is 5. Okay, so d phi is equals to the dl cross r. Okay, so the DL is the direction of the current flow in the Z directions, and then you cross product with the R, right? R. Okay, so R is the directions, okay, of the unit of the vector R. Okay, you can see it's pointing in the Y directions, pointing in the Y directions. Okay, so you can see here, you can cancel it, right? You get 1 is equals to 1. Z, Y, you get negative X. Okay, so it is correct. Okay, you can refer back. Okay, so it is correct to say that the H is negative X. Negative X. Now we look at the second conditions. Okay, ask us to find the H at 5 pi over 4 and 0. Okay, 5 pi over 4 and 0. So we'll draw again this very quickly. So the current is this one. Okay, so is observation point is 5 pi over 4 and 0. So obviously this coordinate is not Cartesian. Okay, this coordinate is cylindrical. You would like to know what is the angle here in degree. If you want to know what is the angle here in degree, you can take this thing and multiply with 180 divided pi. So it is equals to 45. So the observation point is see 5, 45 and 0. Okay, so this is the observation point, and this is your vector R. Okay, vector R. Okay, so now again you have to find the point T, right? In this case the point T is still 0, 0, 0. So you can find the R. Okay, but first of all you need to convert the distance, right? Or you convert to equivalent Cartesian distance. Okay, so it is 45 degrees, so you have 5 unit here, 5 unit here, right? Okay, so how to convert it? So how to convert from cylindrical to for polar? In this case, more suitable to be polar. Okay, so this is this is not 5. 5 is the length here, right? Okay, so you can just check it. Okay, like this. This is 5, and this is 45, right? 45 degree, and this position is 5. I would say the length is 5. Okay, so you can find by finding the angle using the sine or cos. Okay, if you want to find this y and x, okay, if you want to find the y, it will be equals to opposite over adjacent. See, opposite over hypotenuse. 5 is equals to sine, right? Okay, sine 45. Okay, so from here you can get the y, what is the value, and then x over 5 is the adjacent. Okay, adjacent over hypotenuse, you have 45. So from here you can get the y, from here you can get the x. Okay, you can press calculator, you get this around 3.53. Okay, and the next one is 5 multiplied cos 45. So make sure you are in the correct angle mode. It is degree. Okay, so these are also the same. 3.53. Okay, so while you already know the coordinate here, this is the coordinate y, this is the coordinate x. Okay, you can proceed to find the unit, the distance. Okay, the distance. This one will be equals to, but the question is telling us the direction is the phi. The direction is the phi. Okay, the direction is the phi. So maybe you won't need to be so complicated because our equation is this: h equals to I over 2 pi r phi, right? So the phi, okay, we don't need to actually know what is the phi. Okay, I equals to 10 pi ampere. Okay, so 2 pi r. R is the distance from here. Okay, from here up to this point. Okay, so the distance is equals to 5. Okay, distance is equals to 5. Okay, so distance is equal to 5. So as a result, you get, yes, you get the phi as your answer. Okay, so this is correct. And then we go to question C. We go to question option number C. So for option C, okay, asking us to find the magnetic field at -340. Okay, so this is the line. We have to repeat many times, so make sure you are familiar with all this. So is -3. -3 is over here, -3, and 4, maybe it's here, and 0. So find this thing. So still this one will be your R. Okay, so your R will be equals to -3, 4, and 0 minus with the point T, right, is 0, 0, 0. Okay, so you have a -3 and 4 and 0, and your magnitude will be 9 plus 16 square root 25 will be 5, and your unit vector R will be -3, 4, 0 over 5. Okay, so this is the things. So when you replace into the equation, so 10 pi ampere over 4 pi r, no, it's not 4 pi, it's 2 pi. It's 2 pi. Okay, so it will be dl is the z directions cross with this -3, -3x plus 4y divide with the 5. Okay, so this is equals to 1. Okay, so you will have zx equals to y, so equals to -y, right, -y. Okay, and 5 over 3 is equals to 0.1, 0.6. Okay, and then 4 over 5 is 0.8, so you have a zy -x. Okay, so this is the answer. Okay, which is correct. Okay, and last one is the D at the position 5, 3 pi over 2, and 0. Okay, so we draw again. Okay, the position is 5, 3 pi over 2. So what is 3 pi over 2? You can find out, okay? You can find out what are them. So it is 270. Yeah? So 270 means that it is over here, right? So the angle is, the length is 5. Okay, the length is 5. Okay, so we'll be using again these equations. So it is the I over 2 pi. See the R is the distance from the point T to the point P. So it's equals to 5. Okay, so this one I replace with 10 pi. Okay, so the answer is negative phi. This is phi, phi. Okay, phi. Okay, so this is 1. Okay, so you will get phi. Okay, but the question is saying that, okay, you can see the questions. The question is saying that, okay, it is equals to negative phi. So this is not correct. So answer is D. Okay. So which of the statement is not the characteristic of a static magnetic field? Okay. Okay, static magnetic field. Okay, this is your magnetic. Maybe I will just put the magnet bar. Okay, so this is your magnetic field, right? Surround the magnet bar. So it is a solenoid. Okay, solenoid. This is the solenoid. Okay, so this is the magnetic field. Is a type of solenoid. This is correct. Okay, it is conservative. Okay, so conservative means that, okay, if you're taking this one, curve with the hedge. Oops. Okay, this curve with the hedge is equals to 0. Okay, so curve of the hedge is not equals to 0. So this is wrong. This is not equals to 0. Okay, it has no sink or source. Sink or source, it means that it has no starting point and ending point. And this is correct because it starts at itself and terminates at itself also. So the magnetic flux lines are always closed, which is correct. Okay, so not the characteristic. So I will pick the B. Okay, we look at the question number 8. So for the current enclosed path of a figure Q8, calculate the line integral of this one. Okay, so this is the Ampere's law. Ampere's law says that if we integrate the magnetic field, okay, in a closed loop, okay, it is equals to the I enclosed by the loop. Okay, you can see this case. Where is the loop? Okay, this is your loop, right? Okay, so your loop, okay, you have to integrate the loop in the line in the closed loop. Okay, so it's equals to the current that is enclosed by the loop. Okay, so the answer will be 10. Okay, because the loop only enclosed 10 ampere. So the answer will be C. The force exerted on a differential length, okay, at point P along the conducting conductor loop in figure 9 is, okay, they want to find the force acting on the length, okay, at point P. So we look at this one. Maybe this one is not that clear. So you have a loop. Okay, so point P is here, right? Point P. So this point P has a length, right? Point P has a differential length here. It has a length here. Okay, this has a length. So you need to find the force. Where's the direction of the force? Okay, so the force, okay, acting on a current, you see this is current, on a current element will be equals to integrate I dl, okay, and cross with the B. Okay, so if you want to know the directions, the main thing would be this dl. Okay, so dl is in these directions. Is in these directions. Okay, so this is B. B is in what directions? B is in, you see the B, going up, right? This is the direction of the B. Direction of the B. Okay, so if the B is going up, you just focus here. If the B is going up, okay, this one, the differential length is going in this way. In this way. You can see this way. Okay, this way. This way, if you break it to be, alright, maybe I will put the coordinate systems so it is easier for you to see. So this is the directions. It's a combinations of the x and also the y. Okay, So the DL, okay, now I talk about the direction only. The DL, the directions, is equals to, okay, first of all, it is negative x, right? And then y, and then y. Okay, and the B directions is equals to, I would say that it is z. It's z. So if you cross product this thing, okay, negative x plus y, and then you cross product with the z. So what will happen? So xz will give you negative y, negative, negative, positive y, right? So yz give you positive x. So where is the positive y and positive x? Okay, so positive x will be this direction, right? Okay, plus the positive y. Okay, so this one will be the directions, like this. This one will be the directions. So this one will be the direction of your force. Okay, so you see which one, okay, is describing these directions. Outward along OP. OP is here, O and P. Outward along OP. Okay, which is the same as this. Okay, so the answer is this one. Inward is not correct lah. In the direction of magnetic field, boom is not correct. Tangential to the loop. Tangential means like this. This is tangential. Okay, so it is not correct also, right? So the answer is A. Okay, we go to the next one. Which of the following statements are true about a magnetic line? Magnetic lines start from the south pole and end at the north pole outside the magnet. This is not correct, okay, because the magnetic field start from the north and ends at the south outside the magnet. Okay, so this is not true. Magnetic lines are continuous. Yes, continuous. They never intersect each other. Yes. Inside the magnetic field line are directed from south to north. Inside is directed from south to north. Okay, so this one is correct. Okay, so answer is B. So figure 11 shows two identical bar magnet fixed at a place with a proton moving to the right about to enter the region between two magnets. Which statement will best describe what happened to the proton while traveling across the things? Okay, so what happened? So now when this thing travel, it has the U, right? It has the speed. And for the magnetic bar, it has the magnetic fields around it, right? So you can see the magnetic field in the, I will put a reference here, X directions. Okay, and this is Y directions. Okay, if you know what happened to the proton, right? See, so the proton, you might suspect it will experience the force. Okay, so if you want to know what is the force experienced by the proton, you can use this formula, U cross B. U cross B. So you see the U, the U directions, the U direction is X directions, because it's moving to the right, X direction. And the B direction also moving in the X directions. B also in the X directions. When the X cross product with the X, it is equal to 0. Okay, so meaning that this proton doesn't experience any force when it entered the region. So it will continue straight until the end. Okay, so you can see, so the most suitable answer will be the B, because A is curved downward, right? C is curved upward. Okay, proton stop. Okay, no, it will still continue to move because it has velocity. Okay, move to the right in a straight line. Okay, so this is correct. So 12, which of the following is the definition of Faraday's law? It is a basic law of electromagnetism which demonstrates the interactions of magnetic flux and the induced voltage in a closed circuit. Alright, this one seems is okay. It is defined as the relationship between the current distributions and electric field intensity. So Faraday's law doesn't relate to these things, so this is wrong. It is a combination of two different field components in normal and tangential directions. Also not related. So this one not related. The answer is A. So 13. Mr. Faraday and Mr. Joseph Henry had conducted numerous experiments both in London and New York respectively and discovered the following. What they find out. Electric current density is directly proportional to the conducting. Oh no, this is not about this because it is Faraday. Okay, Faraday is about the magnetic field, right? Okay, magnetic field can induce an electric current in a closed loop, but only if the magnetic flux linking the surface of the loop change with time. This is correct. Uniform magnetic field distribution can be generated on a filamentary wire. Yes, magnetic field can be generated if the current has if the wire has current, but this is not true. So EMF can be induced in a closed loop based on galvanometer deflection. It's telling you that if the galvanometer deflect, then you will have an EMF generator. This is not correct. Only when you have EMF, the galvanometer deflect. So the answer is B. If the number of the turn in the coil increase, the induced electromagnetic force in the coil will. This one you have to refer to the transformer EMF formula. Negative N, okay, dt. So we have integrate B dot dx, right? So what happens if your N increase? So very easy. If your N increase, the other one will also increase. The transformer EMF will also increase. Okay. What of the galvanometer shows that the flow of induced is detected along the square loop? Choose the correct answer to fill the blank. Okay. So the first one, option momentary deflections. Okay, flow of the detected in the. Okay, so this one obviously galvanometer you use to measure the current, right? You use to measure the currents. Okay, so answer is A. Skin depth phenomena is found in which material? Okay, skin depth is the how deep the electromagnetic wave can penetrate. Okay, until the intensity is around 0.36. Okay, of its original. Okay, so the answer is penetrate in conductor. So the electric field component, okay, of a wave in free space is given by this. It can be concluded that wave propagate in the negative z directions. No, it is positive z. This is wrong. Wave number is 0.33. Here, wave number is the k. So you have to calculate. How to calculate the k or the beta? Beta is equals to 2 pi f, right? 2 pi f. Okay. So you have to calculate what is the f, right? So how to calculate the f? Okay, C equals to F lambda because this is a free space. Okay, so your F you could replace by C over lambda. Right, you take this thing. Oh, no, the formula is wrong. It's not the F, the formula is lambda. Okay, the formula is lambda. So, or there are two ways, this one, or you use omega over speed. speed of the wave. I think this one better. Okay, so you can divide. Omega is 10 power 8. The speed is 3 times 10 power 8. Okay, so you can calculate the answer. What is the answer? 10 power 8 divide with 3 times 10 power 8. Okay, so you have this milli, 333 milli, 333 milli. So this is correct, 333 milli. Okay, so if you change it to meter, so it will be 0.33. This is correct. So the wavelength, okay, you can calculate the wavelength. Okay, so wavelength is equals to what? C equals to F lambda, or you want to calculate from here. Okay, you can calculate from here. So if it is lambda is 2 pi, okay, 2 pi over 0.33, okay, is 19, 0.333, okay, 0.333, right? Okay, so it is 18.85, something like that. Okay, and the wave amplitude is 10 millivolt per meter. 10 milli, right? 10 milli. This is just 10. There is no milli, so this one is not correct. So the answer is 2 and 3. So given that the H is equal to blah blah blah, which of this statement is not true? Okay, so you can check. This is correct. Okay, and this is correct also. And this you can check here. Where polarized along the Z directions. Along the Z direction here. Okay, you can see it's not along the Z directions. Okay, so it is along the X direction, so it's not true. Okay, so 19, what is the major factor in determining whether medium is a lossless dielectric or lossy dielectric or good conductor? Okay, so you know, right, to determine these mediums, you have to look at the conductivity, you have to look at the permittivity, you have to look at the mu. Okay, so loss tangent is equals to omega sigma over omega epsilon. Okay, so this one is also related. Okay, so you have to pick this one, or you can pick this one. You have to answer for this. Okay, last questions for part A. So a blue beam of light that fall on two narrow slits produce an interference patterns on a screen. Okay, so this one is an experience or an experiment related to double slit. Double slit, it means that you have a surface, but on the surface you have two holes. So when you have a light, this is the light coming from the source. Okay, when it sees these two slits, okay, it will interfere in this way. Okay, it will interfere in this way. And this one also, it will interfere in this way. Okay, so at the position where these two waves that intercept each other, okay, this one will generate I would say it will generate a positive or maximum light. Okay, it will generate maximum light. Okay, so here you will have maximum light, okay, maximum light here. So whereas for this region, right, you will have a minimum light. Okay, so this thing continuously, maximum, minimum, maximum, minimum. When you put a screen over here, you can see this effect. Okay, maximum here, maximum here, maximum here, and minimum light in between. Okay, so it's asking if a red beam of light is used in the same experience. Initially, you're using the blue. After that, it changed to red. Okay, which changes can be observed in the interface pattern. So when you change the light, it means that you change the wavelength. A different light has different wavelength. So the wavelength for the red line is greater. Do again. Is greater than the wavelength of the blue light. This is red. So when you have greater wavelength, it means that the gap in between will be greater. Okay, so interference fringe move closer to the center. Okay, what is the wavelength? If I say the wavelength, this, for example, if this is the blue one, okay, the wavelength for the red one will be greater, right? So it will be greater like this. So this thing will tell you the gap. Okay, the gap in between the next one will be greater compared to this one. Okay, if for blue light, okay, so the gap between the peak will be like this. But if for the red line, the gap between the peak will be this one and this one. You see, they are further away. So as a result, the gap over here will be also greater. Okay, so which one? In the move, either is closer or away. Because this one is no change, right? Okay, no change. Okay, this is bright fringe are replaced with dark fringe, is not correct. Okay, which one? Okay, so when you have a greater wavelength, it will move away. The gap will be greater, move away. So the answer is C. Alright, so this is part A. Okay, so let's look at the part B questions, subjective questions. So you have a spherical capacitor is formed by two metallic spheres of radius A and B as shown in the figure Q1b. Okay, so this is your figure Q1b. Okay, the region between the two metallic spheres is filled with dielectric with a dielectric constant of epsilon r. Okay, you see where is the epsilon r? This is the epsilon r. So the charge on the inner sphere is positive and the outer sphere is negative. Okay, so this inner is positively charged. So you have positive charge. And outer you have negative charge. Okay, state the law that can be used to find the total electric flux. Okay, the total electric flux is this one. Okay, electric flux in the region between the sphere. Okay, so when you talk about the electric flux, okay, so the law that will be used is this Gauss law. Okay, integrate the electric flux density across a surface, okay, will be equals to the charge enclosed by the surface. Okay, so this itself is the way we find the total electric flux. Okay, because this one is equal to integrate d dot ds. Okay, d dot ds. So the answer is Gauss law. Gauss law. Based on your answer in the section A, sketch a diagram represent the use of the law in spherical capacitor applications. Okay, so you can sketch this thing. And sketch. Okay, this is your outer conductor. And you sketch your inner conductor. Inner conductor is positively charged. Outer conductor is negatively charged. Okay, so the electric field, okay, will be oriented in this way. Right, you can label it. Okay, so electric field will be in this way. Okay, so you can put down this Gaussian surface if you want to find the electric flux here. Okay, this you can label it as Gaussian surface. Gaussian surface. Okay, Gaussian surface. Okay, so this is how we use the Gauss law. Okay, we have the Gaussian surface. We can find the electric flux, okay, at a position in between the inner and outer conductor. Okay. Alright, we look at question number C. By using the law that is stated in the Q1, prove that the general formula to calculate the electric field intensity in the region between the sphere is this one. Okay, so this formula represents the electric field between the inner and outer sphere. See, okay, so you have the outer conductor and you have the inner conductor. Okay, because the inner is positively charged and the outer is negatively charged, so the electric field will be in the outward directions, right? Outward directions. So the formulas over here is telling us the electric field in between the inner and outer, okay, which is the electric field in these regions, okay, electric field at all these positions. Okay, to find the electric field at all these positions using the Gauss law, the first thing is we have to construct the Gaussian surface. Okay, so this is the Gaussian surface that I already construct, and then we will apply the Gauss law. Okay, so the Gauss law says that if we integrate the flux, okay, across the Gaussian surface, we will be able to get the charge that is enclosed by the surface. Okay, so first of all, this is a surface integral, so the directions of the D would be in the R directions. Okay, because we are using the spherical coordinate systems. And then for spherical coordinate systems, okay, the ds in the R directions will be R squared sine theta d theta and d phi. Okay, in the R directions, and it is equals to Q. Okay, so the R and R dot product will give 1. Okay, we define the interval of the theta. Okay, so the theta will be from 0 to pi. Right, phi will be 0 to 2 pi. Alright, 0 to 2 pi. So as a result, okay, we will get d r squared, right? It's a common one, 2 and 2 pi. Okay, I skip the steps. Okay, if you think you need to integrate properly, you can do so, no problems. So you will get 4 pi r squared and d, right, equals to the q. Okay, so your d will be equals to q over 4 pi r squared. Okay, and we know the relationship between the d and e, right? D is equals to epsilon e. Okay, so if this is the e, okay, so this equation will become q over 4 pi epsilon r squared. Okay, so the direction we can insert it. The direction is the r, right? We already defined the direction is the r. So from here, okay, we already proved that, okay, the equations is equals to this one. Yeah, this one. Okay, so you can say that it is proven. Right, so we go to the next questions. Find the general formulas for the coaxial capacitor, okay, it shouldn't be a coaxial, it is actually a spherical. Okay, spherical capacitors electric potential V. Okay, once we get the E, okay, we can find the V. Am I right? Okay, so for this one, okay, no matter you're able to get this E or not, okay, we don't care whether you can get this E or not, but when you want to find the V, okay, by using the equation integrate E dot dl, okay, so make sure you use the equation this. Don't use the wrong equations, otherwise you will lose mark in both part. Okay, because this one when they ask you to prove, confirm is correct one. Okay, so go down. Okay, so V equals to integrate negative E dot dl. Okay, what's the meaning? What we are doing? Okay, so we have an inner conductor, outer and inner sphere. Okay, electric field is this way. Okay, so if we integrate the electric field, okay, across the length, this is the dl, this is the dl. Okay, we will be able to get the voltage. Okay, so if we integrate E, okay, so the E is Q over 4 pi epsilon naught R square. Okay, in the R directions. Okay, in the R directions, dot product with the, you see the length is in the R directions. Okay, so we use the dr and R directions. Dot product give you 1. Okay, so you will integrate from positive terminal to negative terminal. You integrate from negative terminal to positive terminal. Okay, so negative integrate B to A. Okay, and you take out this thing. This is a constants. Okay, I split the constants and also this R square dr. Okay, or maybe I write in this way, R negative 2. Okay, so you will get negative Q over 4 pi epsilon naught. So you get R plus 1 over R negative 1 over negative 1. Okay, and A and B. Okay, so negative become positive, 4 pi epsilon naught. So it is 1 over A minus 1 over B. Okay, so this one will be the V, the potentials between, okay, the inner and outer sphere. Okay, and then calculate the capacitance. Okay, capacitance, which means that you have to apply this formula. Wait, this is what? This is D and E. So this is D and the E is here. Okay, so capacitance, the general formula will be this. Right, so the Q you remain. Okay, while the V will be equals to divide V, right? So you will have this 4 pi epsilon naught divide Q 1 over A minus 1 over B. Okay, you can cancel the Q, and then you get 4 pi epsilon naught divide 1 over A minus 1 over B. Okay, so this is the equations of capacitance, okay, spherical capacitance. Next is this question 2. So you have two infinite, okay, current filament as shown in the figure Q2. Okay, you can look at this, is figure Q2 infinite currents. You have I1 and I2. Calculate the magnetic field at 003. Okay, 003 might be somewhere here. Okay, 003. Yeah, this is the observation point. Okay, if the directions of both current filaments is along the zag. Okay, so this is the direction of your current. Okay, and L1 and L2 is 3 unit. Okay, L1 and L2. L1 is the distance from the origin until here is 3 unit. Okay, and L2 is also 3 unit. Okay, 3 unit. So I1 is 2 ampere and the I2 is 4 ampere. Okay, so this is the information that you have. Okay, so find the what? The magnetic field. Okay, so you have to know what equations to be applied. Okay, this is a infinite line, so the magnetic field is equals to I over sorry, it's not 4, it's a 2 pi r and v. Okay, so what is the r? Okay, so now you have a 2i, am I right? So you are going to have a hi, a h1 and also the h2 for you to get the h total. Okay, you have h1 and also the h2. Okay, so we look at the h1. Okay, so the h1 is equals to the I1, right? I1. So you have a I1 which is 2 ampere. Okay, 2 ampere. 2 over 4 pi r. So r is the distance between the observation point and also your point T, right? So in this case, okay, your point T will be here, am I right? Okay, so the distance, so the distance means that, okay, this will be a distance. Okay, so this distance is the same as 3, as 3. So but anyway, if you want to calculate, it's okay. You can take the coordinate of point T and point P, and then you calculate. So the coordinate of point T is the 0, -3, and 3, right? Okay, because the observation point is 3 over here. Okay, so this is the point T. If you want to calculate R, is also okay. Okay, -3 and 3. So over here, you will have your R equals to 3. It's not 4, sorry, it's 2. Okay, and phi is represent the direction of the current cross with the R directions. This is DL cross with the R. Okay. Okay, so the DL is the direction of current flow in the Z directions. And for the R, okay, so this is your R, right? What we always calculate. This is your R. So your R is in the Y direction. You see the arrow, okay, is pointed towards the Y. So you have Y directions here. Okay, so this is your H1. So you can calculate it. Okay, zy is equal to negative x. Okay, zy is negative x. So for this one, you have a 1 divide 3 pi. So it is 106.1 milli, milli ampere per meter. Okay, milli ampere per meter. And for the H2, okay, you can calculate H2 using similar method. So for the H2, okay, the I2 is 4 ampere. Okay, it's 4 ampere over 2 pi r. Okay, so in this case, your r, okay, will be the distance from point T here. Here also got point T. Point towards the observation point. So in this case, your point T coordinate is 0, 3, and 3. Okay, you can find the distance. So this is your r. So the distance is 3. Okay, distance is 3. Okay, dl is z directions. Okay, and this unit vector r is negative y directions. Negative y directions. Y is negative y. You look at r. Okay, this one is the same direction as this, the r here, the r for the I2. Okay, and the arrow is pointing to negative y directions, so it is y. So you can calculate the answer. So zy, you get positive x. Okay, positive x. So calculate 2 over 3 pi. Okay, so it's 212, okay, 0.2 milli ampere per meter. Okay. So 212.2. Okay, you can see this is a double of this, right? Because of the current. Because of the current, it is double of it. Okay, so now you can find the H total, which is equals to 106.1 plus 212.2. Okay, so you get this 318.3 milli ampere per meter. Oops, sorry, they are in the different directions, so I cannot add it. So the answer will be minus, right? 212 minus the 106. So it's 106. Okay, so this is the H total. State two ways. Okay, two ways. Okay, to determine the zero magnetic field at these positions. How to make the total magnetic field to be 0? So now the question is how to make the magnetic field to be 0. As I explained to you just now, you can see, okay, this is double of this. If you want to make it 0, you have to improve the current. Okay, you can increase one of it. How to make it 0? Increase the current I1 to 4 ampere. Okay, so this is one of the way. Okay, the other way is, okay, beside the currents, right, beside the current, we have one more variable, which is the distance. Okay, so if you want to increase, because you want to make it 0, right? Okay, so if you want to increase this H1 so that it is equals to 212, okay, you have to reduce. You have to reduce the distance. The distance of I1, okay, with the observation point. Okay, so you have to reduce. Okay, so you have to reduce the distance between I1 and observation point. Observation point. Okay, so you can give example to make the coordinate. For example, okay, I1 no, L1, sorry, I would say L1 is equals to 1.5 unit. Okay, so when you change it to 1.5, okay, because it is double, right? Okay, you will change it to 1.5. Okay, so it will be 1 over 1.5 pi. 1.5 pi. Okay, so you can have the answer. Okay, so there are many ways. Either you want to explain this one, okay, you can increase the distance for I2, okay, or you reduce the current of I2. Okay, because they just mentioned two ways, right? Okay, so you can mention two ways as long as it is reasonable and correct, and it will be accepted, right? All right, we go to the question number 2C. So by ignoring the value given in the question 2A, okay, you have to ignore, okay, determine the force per unit length acting on I2, okay. Force per unit length acting on I2 means that you need to find the F2, okay. If the I1 is 6 ampere, I2 is 8 ampere, and L1 plus L2 equals to 10, okay, with both current flowing in the same directions. Okay, so we try to draw this thing up first. How does it look like? Okay, so this is question C. Okay, so we have these coordinate systems. Okay, and then we have the currents. Okay, this is our current, so we have two currents. Okay, so the I1 is 6 ampere. This is the I1, which is equal to 6. Okay, and then the I2 is equals to 8. So L1 plus L2, okay, L1 plus L2 means that, see this, where is L1 and where is L2? So the separations between them is 10. Okay, meaning that from here up to here is 10 unit. Okay, and then with current in all directions, in the same directions. Okay, so you are required to find the F2. Okay, so F2. So F2 is the force acting on the I2. So now your I2 is exposed to the magnetic field. Okay, to the magnetic field which is produced by I1. Right, your I1 has current flow, so that it produces the B1. Okay, so our F2 will be integrate the I2 dl, okay, cross with the B1. Okay, so B1 will be the magnetic field from I1. Okay, so from I1, which means that you have to write in this way, cross with the B1. So you have to use the Ampere's law. So you have a I1 here over 2 pi r, okay, and the phi. Okay, so this one will represent your B1, yeah, it will represent your B1. Okay, so let's fill up the blank. Okay, so you integrate. So the I2 is 8 ampere. Okay, so the length of your I2 is depend on the axis Z. So this one will be dz and z directions. Okay, so the length will be from like negative infinity to infinity, right? Okay, this is the length. So infinity is here, negative infinity is here. Yeah, I2. Okay, and then for the I1, okay, the value of the I1 is 6 ampere. Okay, so 2 pi r. So r is the distance. R is the distance, okay, from I1, okay, to I2. Okay, this is a distance. So the distance is 10. Okay, phi is the dl. dl is the direction of the current I1. So your current I1 is flow in the z direction. So the dl is the z directions. Cross with the unit vector r. Okay, so unit vector r is the directions of point from I1 to the point that you want to find the magnetic field. Okay, so obviously this one is the y directions. So you can put y directions here. Okay, so now we can calculate. So first of all, maybe we settle the cross product of this. So zy, you get a negative x. Right. Okay, so this one is 6 divide 2 pi multiply 10. Okay, so you get, oh yeah, we have the epsilon. No, we have the mu naught, right? There is a h, so we will have a mu naught here. Okay, wait, multiply shift constant, the mu naught, okay, is equals to 75, 76. I could just say that this one is 76 k, kilo. Okay, kilo. Okay, so here you have a dz at dz and z. Okay, so now we have the cross product, okay, for the zx. So zx you get positive y, but because of the negative you get negative y, right? Okay, and then from the 10 meter 3 unit 10 meter, okay, the separation is 10 meter milli. The separation is milli or meter? 10 meter. Okay, so okay, let's calculate. 76 times 8. So you have a 608. Okay, 608. Okay, so this one will become, okay, so this one specifically refer to the length. This one is the length. Okay, so this one is k. This one is your force. Okay, so kilo newton. Okay, so the force per unit length, okay, will be equals to this. Okay, so you can cancel this part to get 608, okay, kilo newton, and is in the negative y directions. Negative y, you want to put negative here. Okay, you can put negative here. So this one will be the answer. Okay, 608. Okay, so this is question C. Question D. If the current in I1 and I2 are in opposite directions, predict the direction of the force acting on the I2. Okay, opposite directions. So we refer back to the force, okay, that we have calculate just now. We have the I1, right? Okay, so we have the dz, okay, the z directions. Okay, no, this is not I1, this is I2. Okay, and then we cross product with the I1 over 2 pi r, right? So the dl is also the z directions and cross product with the unit vector r, which is y directions. Now they are asking you if the I1 and I2 are in opposite directions. Opposite direction meaning that one of it could be negative z. Okay, so when you continue the calculations, you will still get the same thing for the F2, right? Except for the directions. Just now the direction is negative y, so now probably you will get 608, okay, kilonewton, and it is in the y directions then because of this negative. Okay, so you can mention that what predict the directions. So the directions of the force will be positive y. Positive y. Okay, so you can just mention stuff. Okay, you can just mention. Now we look at question number 3, which is about Faraday law. 3a. Faraday law states that the induced electromagnetic force, the EMF voltage in any closed circuit is equal to the rate of change of time of the magnetic flux linkage by the circuit. With an aid of a diagram, discuss the experiment setup used to verify the Faraday law. So this one is asking you to use a diagram to show, okay, how to verify the Faraday's law, how to prove the electromagnetic force is generated. Okay, so you could use the setup something like the video that we have watched earlier in class. Okay, so you could have a coin. Okay, so this is a coin. So you can draw a coin. Okay, so this one you got the coin. So the coin is connected to the galvanometer. Okay, so to measure the deflections. Okay, so you can see, or you can put ammeter, ammeter. Then so you can label this is ammeter. Ammeter. So you can put a magnet bar. So you can label S, N, and X. Okay, so you can put the directions. Okay, something like this. So you can do, after you draw this thing, right? Okay, you have to do some explanations. Okay, what happened? So when the magnet bar is moved into the coin, okay, there is deflections, okay, on the ammeter, okay. When the magnet bar is pulled out, the deflections will be in the opposite directions. Okay, opposite directions. Okay, so this shows what? Okay, so this shows that when the magnetic field is changed, okay, with respect to time, it generates okay, the current in the loop. Okay, so this one is the thing. So you can draw a diagram, okay, and do some explanations. Okay, so you can get these 4 marks. Okay, so you have a sliding bar as shown in the figure Q3B. Okay, so Q3B looks like this. This is a sliding bar. So this sliding bar is located at the position X. X equals to 10T plus 4T3, and the separation between the two rails is 40 cm. So if the magnetic flux is equals to this one, okay, to this one, okay, compute the voltmeter reading at the time 0.8, okay, 0.8. So the first thing that we have to do is we have to identify whether this is a motional or transformer EMF, right? Motional or transformer EMF. So this one is obviously the motional EMF. Okay, motional EMF, because you see the sliding bar is going to move. So the equation of the motional EMF will be U cross B dot dl. Okay, U cross B dot dl. Okay, so what is the U? Okay, what is the U? They didn't give us the U, right? But they give us the X. They give us the X, and it's okay. You can just left the U here. Okay, U cross with the B. Or we want to replace the U. Okay, replace the U. Because the U is equals to the distance over time, right? So the distance is given, right? What is the distance? So the distance is 10t plus 4t power 3 power cube, divide with the t. So you will have a 10 plus 4t squared. Okay, so this is your U. Okay, so you can put your U, that is the 10t plus 4t squared. Okay, so the directions of the U, you can refer to the drawing. Okay, you see the sliding. Okay, so the U, okay, is in the X directions. Okay, so you can put X directions. Cross with the B. This one, cross with the B. Here, okay. So cross with the B. So what's the B? The B is 0.8 x squared. Okay, 0.8 x squared in the Z directions. Okay, so DL. Okay, so DL will be the length of the current. Okay, see, this is current is going to flow here. Okay, it's according to the axis Y, so this one will be dy. Okay, because you have a dot product. Okay, so it will be Y directions. Y directions. Okay, so next we are going to define. Okay, we are going to define the interval. Okay, so we have to refer back to to our drawing. So you see our B is going up, so the current is going to generate another B that is going down. So if you use your finger, so the current will be going in the from A to B. Okay, so you have to integrate from B to A. Okay, so from B to A, so B obviously is 0. A is 40 centimeter, which is 0.4. Okay, so you integrate from 0 to 0.4. Okay, the Y. Okay, so here you don't have the Y. Okay, never mind. So let us put this thing. So first of all, we do the cross product between the X and Z. So X, Z, give you negative y, right? Negative y, so you will have a negative y here. Dot the dy and y. Okay, and then the x square over here, okay, you can consider to expand it. Okay, you consider to expand it. So it could be integrate 0.4. So 10, wait, u is 10 t squared, so don't have the t. Okay, so you have a 10 plus 4t squared, right? Okay, multiply with the 10t plus 4t cubed. Okay, and then you still have the 0.8. Okay, still have the 0.8. Multiply with the 0.8. Okay, so negative y and y will give you negative 1. Okay, negative 1. So the answer will be the multiplications of this 4t squared 10t plus 4t, oops, this is not cube but this is square. Okay, 4t squared. Wait, what is the x? What's the x? The x is okay, then cube. Okay, kuasa 2 cube and square 0.8 multiply 0.4, you get 0.32, and you have a negative, right? You have a negative. Okay, so this one will be your motional EMF. Okay, you can leave your answer in this way, or if you want to multiply is also fine, but this is not complete yet because you need to find the value at the t equals to 0.8. Okay, when the t is 0.8, so 0.8. Okay, so you have a 10, 0.8 plus 4, 0.8 cube, and then power 2, and 0.22. Okay. Yeah, so let's calculate. Okay, so the answer is 405.79. Don't worry about negative, you can just include a negative. Okay, so this one is the answer. Alright, the last questions. Seawater plays a vital role in the study of submarine communications. So if the constitutive parameter of the seawater is given by all these, okay, so these are the constitutive parameters, and the frequency is 100 megahertz, shows that the seawater is a good conductor. Okay, seawater is a good conductor. So if you want to show that seawater is a good conductor, you have to make sure that this one is greater than omega epsilon. Okay, so calculate the attenuation constants and also the phase constants. Okay, so if they are good conductors, so their equation will be equals to square root pi f mu and sigma. Okay, so this is the equations. So the wave velocity So the U, okay, you can get it by omega divide with the beta, the wave velocity, okay, and the wavelength, wavelength you can calculate from here, 2 pi over lambda, okay, 2 pi over lambda, okay, or you can calculate based on U equals to F lambda also, okay, same things. Skin depth is equals to 1 over alpha, okay, 1 over alpha, and the intrinsic impedance, okay, the intrinsic impedance equation, you can refer to your slide. What is the equations for the intrinsic for good conductor? Okay, so for the good conductor, the intrinsic the impedance will be omega mu over sigma, okay, and the angle is 45 degree. Or if you don't want to calculate using this one, you can calculate using J omega mu divide with sigma. Okay, so this is the intrinsic impedance of a good conductor. Alright, so let's calculate it. So for the A, okay, you have to prove. So this one, you have to calculate. Okay, so for the sigma, the conductivity is equals to 4. Okay, and the omega is 2 pi f. The f is 100 mega and epsilon naught. Okay, so you can calculate 2 pi multiply 100 mega. Okay, multiply. Okay, so this is 5.56 milli. So of course the 4 is greater than this 5.56 milli. Okay, so the seawater is a good conductor. Alright, good conductor. So for the B, okay, so B is calculating the attenuation constant and phase constants. Okay, so the formula that you have to use is pi f sigma and mu. So your pi, the f is 100 mega, the conductivity is 4, and the mu r is equals to 1, so they just have the mu naught. Okay, so you can calculate square root 100, okay, multiply with pi 4 and multiply with the mu. Alright, okay, so you get this beta is equals to 39.74, okay, same as the alpha. Okay, and then for the C, you have to calculate the wave velocity, and wave velocity is omega divide beta. So this is 2 pi f 100 mega, or divide with 39.74. Okay, so 2 pi, okay, 39.74, okay, is 15.8 mega, okay, meter per second. Okay, this is the speed. Okay, and then the D is wavelength. Calculate the wavelength. So the wavelength is equals to 2 pi over beta. So 2 pi over 39.74. So 2 pi 39.74. So it's 0.158 meter. Okay, and then for the E, calculate the skin depth. Okay, the skin depth is equals to 1 over alpha. Okay, so the alpha is the same as the beta. So 1 over 39.74. 1 over 39.74. So you have your answer is 25.16 millimeter. So this is the skin depth. And calculate the intrinsic impedance. So the intrinsic impedance is equals to 2, write the formula first, omega mu over sigma. Okay, so the angle is 45 degree. Okay, so it's 2 pi f 100 mega. Okay, mu naught divide 4. Okay, so the angle is 45 degree. Okay, so 2 pi. Okay, divide 4. Square root answer is equals to 14.04 or 05. And then 45 degree. Alright, so this is the intrinsic impedance. Okay, so this is the solutions for this final exam. Okay, so this is the revisions, okay, for your final exam. I think every one of you would like to know more about the final exam, right? So I'm going to give you some hints. Okay, you can jot down the hints. Okay, so first thing is whatever that is included in the test, it won't appear in your final exam. Okay, so you can start from the Gauss law because it is not covered in your test. Okay, you can start from the Gauss law. So we have one questions from each of the chapter, and here I want you to take note that there is no objective questions. All are subjective questions. There are 4 questions. Okay, no objective questions. Okay, so for the question 1, it is from the chapter 1, electrostatic. Okay, so we have learned about capacitors, right? 3 types of capacitors. Okay, so do you understand each of the capacitors? If I give you the values, are you able to calculate the values? Okay, you have a parallel plate, you have a coaxial capacitors, you have a spherical capacitors. Are you able to calculate? And next one, okay, Gauss law. Okay, do you able to use the Gauss law to define the equations of the electric field? Okay, so what is the procedure? What you have to do first? Okay, make sure you understand the process. Okay, if I give you a structures, are you able to show me what is the electric field equations of that structures? So it can be many structure, it can be cylindrical structures, it can be spherical structures. Alright, so this is all about the chapter 1. Then we go to chapter 2, that is about the magnetostatic. Magnetostatic, we talk about Biot-Savart's law and Peirce's law. Do you know what are them? Okay, do you know how to determine the directions? And do you know how to calculate the magnetic field? Okay, so magnetic field, you can have a finite line, you can have a semi-infinite line, and you can have an infinite line. Okay, do you know how to use the equations? Okay, make sure you know how to use the equations. And yeah, we talk about the force, right? The force acting on the charge, force acting on the current filaments, okay, and force in between 2 current elements. Okay, this is something you have to study as well. Okay, force acting on the current filaments. Right, chapter 3. Yeah, chapter 3, we talk about the transformer EMF and motional EMF. Are you able to tell whether they are transformer or motional if I give you the informations? Okay, how to perform, how to calculate them. Okay, so that is about the questions number 3. Okay, Faraday's law. Last question is question chapter 4, electromagnetic wave propagations. Okay, so you have so many things to calculate. Am I right? Okay, are you able to calculate skin depth? Able to calculate the attenuation constant, the alpha, the beta, determine the direction, determine the intrinsic impedance, wave velocity. So if I give you a medium, are you able to judge whether they are good conductor or lossy dielectric or lossless dielectric? Are you able to judge them? Okay, so this is the question in the chapter 4. All right, okay, so these are some hints and tips for your final exams. Okay, good luck to you all.